Let me talk about how they discovered expanding space. Um, Before Hubble and before anybody really thought about this, um, basically the universe was assumed to be infinitely large and infinitely old because, well, I don't know, it was at least big, right? But this is Olber's paradox, right? And this was on an IB test. But this is the paradox, right? If you have an infinitely old universe and it's infinite in size, then every star in the universe is visible because it's had the light from that star has had an infinite time to reach us. So therefore, if we can see every star, if you think about this, if you think of shells, if you divide the universe into these shells, it's sort of a calculus concept, right? Um, the area of those shells is, of course, 4 pi r squared, right? Okay. And so the number of stars in a particular shell increases with the radius squared. And of course, the intensity decreases with 1 over r, right? So the brightness is some intensity divided by r squared. That means that the shells are the same brightness. And if there's an infinite number of them, then the sky should be infinitely bright, right? Okay, so it would also be, by the way, kind of hot, right? So at night, if we looked in the night sky, every line of sight would end on a star, and we could see those stars, and there wouldn't be any dark places. And so the night sky should be as bright as the surface of the sun. But it's not, right? And of course, the reason that it's not is that the universe is not infinitely old and it's not infinitely large. And we know that now, but that was the paradox back then. Okay. Now, setting the stage for the discovery of the expansion of the universe, when Einstein came up with his general relativity, right? General relativity predicts that the universe can't be static. It either has to expand or it has to contract, but it can't be a static thing, right? Now, Einstein, of course, and everybody else probably thought that the universe should be static. That is, it's not expanding or contracting, right? So what he does is, the math does not suggest this, but he introduces something called the cosmological constant, kind of an anti-gravity sort of thing that keeps the universe static because he believes personally that it should be static, right? A talented mathematician, because see, general relativity involves four-dimensional geometry and incredibly difficult mathematics. This guy is a mathematician. Friedman's a mathematician, and he actually determined that even with the cosmological constant, right, that the universe would still either expand or contract. Finally, somebody gets Einstein to pay attention to this guy's letters. Einstein realizes that he's right, and this is the greatest mistake of his life. Okay, now what's kind of interesting is that something like the cosmological constant is actually happening, but it's not. I mean, it's not the same thing, right? Okay, so Vesto Slipher, who's from the Lowell Observatory, right? Which, by the way, this observatory was the one that was famously discovered the canals on Mars, right? Okay, and if you're thinking of naming a child of yours, if you're collecting, names for future children that you might have, don't immediately count out the name Vesto, Hey, Vesto, right? But anyway, he's looking at redshift of spiral nebula. Now, what is a spiral nebula? Well, a spiral nebula is now called a galaxy. They weren't called galaxies back then because they looked like these little whirlpools of gas, right? And you have to have a really big telescope. You have to have about a 100-inch telescope, right, to see the actual stars in a nebula, in a galaxy, right? So this is a historic term. The modern term is galaxy, but back in the day, we didn't know that they were galaxies, so we called them these spiral nebulas, right? Okay. And what he did was he discovered that there was a redshift in them. If you looked at those things and you looked at the hydrogen lines, right? Okay, this line is much bigger than the line in the laboratory. This line should match this one, but it doesn't, right? And that line right there should match that one, but it's all shifted toward the red. And so, what this is, of course, is the Doppler effect. What that means is that these galaxies are moving away from us. We're here, right? And those galaxies are going away from us, right? And 36 of the 40 that he looked at were redshifted. Of course, what 4 are not? Well, let's see. Andromeda, large and small. The galaxies that orbit us are not redshifted because they're gravitationally bound to us. So we're orbiting them, right? Now, let's just talk about redshift here. That's what this video is about. This is the real formula for redshift if you're going to do it. And when you get to the book, they're going to give you problems to do. Some of them, if you have a really, really large velocity, if you're bigger than, say, 10% the speed of light, you better use this formula. This is the stupid lame formula that IB gives us to use, okay? And this just sets up a ratio. So this is a linear approximation of this. So this means much, much smaller than the speed of light, right? And then this is the change in wavelength. That's the original wavelength. Right, that's the speed of light, right? And then that's the speed, the recession velocity of this galaxy. And you should have that in your note guide. This example is not in the note guide. Okay, so 486 nanometer line. So this is the original wavelength, right? Comes in at 495 nanometers, right? So it's been red shifted, right? So our change in wavelength is 495 minus 486. 495 minus 486 is 9 nanometers, right? That's our change, right? So now we can go 9 nanometers is to the original one, right? That equals our velocity over the speed of light, right? Okay, so we can, if we want kilometers per second, we can put kilometers per second. I'm going to put meters per second, so 3.00 times 10 to the 8th meters per second. Right, and these are nanometers. And then I'm just going to go 3E8 times 9 divided by 486. Whoops. And I get a lot of 5s, right? So how many 5s is that? These calculators are terribly unhelpful. Okay, so I'm going scientific notation. Clear. Second answer. 5.5555.5 repeating, right? That's a decimal point. Times 10 to the 6th meters per second. Okay. So that's pretty good. And then it would be about 5.56 times 10 to the 3rd kilometers per second. We tend to use kilometers per second for recession velocities because of when we get to the Hubble law. Okay. Here's the one that's in your note guide. Let's see. What is the change in wavelength of the 656 nanometer line of a galaxy receding at 20,000 kilometers per second? So let's find the change in wavelength. Is to the original wavelength, right? As 20 kilometers per second, right? And then since that's kilometers per second, I better go 3.00 kilometers per second, right? That's the speed of light. C is equal to 3.00 times 10 to the 8th meters per second, or 3.00 times 10 to the 5th kilometers per second, right? So just be careful of that. A lot of kids have made mistakes with that. So this is easy. I'm going to go 20,000. Did I do it? I did. Divided by 3E5 times 656. And I get that the change is 43.7. 73. Repeating nanometers, right? And it's a redshift. The thing is receding. It's going away from us. So we know that the wavelength gets longer because the frequency gets lower, right? So the new wavelength is 656 plus 43.73 repeating, right? So I'm going to go plus 656, and I'm going to get 699.73 repeating nanometers, which, how many sig figs do we have here? About 700 nanometers, right? Okay. This is stretching it, okay? 44 parts of that. That's getting close to 10% of that, right? 65.6 nanometers would be 10% of that. So our approximation's not so good, okay? Yeah, all right, there's that. Try that relativistic one. That'll give you a better, this guy here, right? This will give you a better wavelength shift, right? It was 20,000 right? So we go 656 square root of 1 plus 20,000 over 3e5, 1 minus 20,000 over 3e5, right? Just toss those in there, right? 656 times the square root of left parenthesis 1 plus 20 divided by 3e5, right parenthesis divided by left parenthesis 1 minus divided by 3e5, right parenthesis. Wow, that's hard to type in. Right, and you get, when you do this, you get 701 nanometers. Right, so we're already off by a little bit, right? Anyway, that's that. There's another example problem that you probably don't need to do, but you do need these notes. So there you go.